Okay, welcome back everyone for the final talk of this morning session. And I'm very pleased to introduce Daniel Fadel, local here to Rio, who's going to be talking about stability of critical points of the self-dual Abelian-Yang-Mills-Higgs energy on Kähler manifolds.
Thank you very much, Jason. Thank you for reading this very long title. So hello everyone, happy Pi Day. I think this is today's 3/14, right? First I would like to thank the organizers for inviting me and for organizing such an amazing event. I'm very happy as a Brazilian mathematician that this conference took place here in Brazil. And I hope to see this in the near future, more conferences like this. And I actually volunteer myself to help to organize more of those. So first,
we will remember.
Okay. So two disclaimers about the contents of my talk. So first, this work initially was part of this joint project, bigger project with Lucas Ambrosio and Gonçalo Oliveira. And Lucas Ambrosio, former student who just graduated, Luciano Jr. But it really took on a life of its own, and actually it became a side project that I focused myself on for the past few months. And really, this is the first actually public announcement of the results of this talk, of this work. There's nothing on arXiv yet, and so it came to my attention. Actually, Henrique Sarep told me, I don't know where he is in the audience, that a student of his, a PhD student called Luis Lara, is actually now in Miami, I think, working with Darin Cheng, and according to Henrique, they are probably thinking about the same problem independently. So I don't know how much of what I'm going to tell you have overlap with this work of theirs. I don't really know what they've done so far. I'm supposed to meet them after the conference. And so let me start by giving you some context. So I hope they are projecting. So yeah, okay. So throughout my talk, MG will be a closed, oriented, and connected Riemannian manifold. And I don't want to talk about the unit circle, so it's at least dimension 2. And L will be a Hermitian line bundle over this manifold. So my convention will be that this Sesky linear form here is a complex linear in the first entry, okay? And I will denote the real part of this guy like this. And for every parameter, positive real number epsilon, I would like to define the following energy functional on pairs consisting of a section of your line bundle and a Hermitian connection, given as follows. So you take epsilon squared of the L2 norm of the curvature, you add the L2 norm of the gradient of U, and then this double L potential term. And of course, with respect to the Riemannian measure, I will omit that. So this is the so-called.
So the first variable is Nabla, and the second variable is U. You mean you haven't actually? Oh no,
it's okay. So this is the self-dual Abelian-Yang-Mills-Higgs energy. And I will explain why this parameter and why self-dual in a moment. For now, let's be pragmatic. So remark. So what are those quantities? So f nabla is, of course, the curvature of nabla. And as you can guess, this is just a two-form with imaginary values. We are in a line bundle. And sometimes I will write f nabla in the physicist notation as minus I. I will times a two-form, a real two-form. So here, these norms are really just where here EI is any local orthonormal basis for tangent bundle. And of course, I use H to compute this norm. And of course, this is just H. And so this functional is clearly U1 gauge invariant. Let me remind you what this means. So,
physics terminology for this.
yeah, sorry. So,
Normally, Yang-Mills theory is explicitly non-abelian. That's why Yang-Mills were distinguished from Maxwell. Also, since
Yeah.
I work at King's College London, we call it Maxwell-Higgs. Because both Maxwell and Higgs were at King's.
oh, okay. All right. So the group of gauge transformations of L is just S1 valued maps. And this is the unit circle in the complex plane. And so if I pick an element here, it is just something like this for some real function. Then phi acts on a pair set as by, sorry. Like this. Right? And then you can see that, for instance, so nabla u goes to E I theta nabla u, and this is the steering invariant. This doesn't change at all, and this is also invariant by this unit. So where? Ah, yes, squared. Sorry, of course. Right. So due to this gauge invariance, you have all the analytic problems. A straightforward calculation shows, so if you compute the first variation of this functional, so this guy is a critical point of E if and only if it satisfies the following second order PDE. Very right? And here, so I times F is now a real two form. This is a one form with real values. This is the real part of the so this is I'm contracting this one form with the real part of the inner product. And of course, here I don't have to bother myself with putting nabla in this D because this is just a two form. And of course, the system is not elliptic due to this gauge invariance, but once you, so of course, there's also this remark that initially you might want to consider not smooth stuff, but weak solutions, weak critical points. But there's a result essentially due to Taubes. But if you want a more updated reference, you can see on Pigatti-Stern paper, more general statement of that, if you, for instance, start with U W12 L infinity section and nabla minus some smooth reference connection in W12, then this is sufficient to guarantee there's some gauge transformation in W22, making your pair smooth. So I will not bother myself with the regularity of solutions. I will just think about smooth critical points. And I just want to make a quick remark about the clear possible absolute minimizer for this, which would be some flat connection with U-nabla parallel and this guy identically 1. But this, of course, there's some topological abstraction for this. So if you have this equal to 0, this is the same as saying that your connection is flat, U is nabla parallel, and this guy is identically 1, which means that your bundle trivializes to the trivial complex line bundle, and your pair U nabla is gauge equivalent to just the trivial product connection and the function U. This bracket notation will be to gauge equivalent class. And actually, if you take a related observation is that if you take U nabla to be a critical point of this guy, then let me number these equations, sorry. 1.1, 1.2, okay? This first equation here, if you compute the Laplacian of this norm squared and use this equation, you readily conclude by the maximum principle that this norm is actually, so sup of this norm is actually less than 1, or else it's identically 1. And in this case, you get back to this situation, right? And here your bundle trivializes, and then you are back to the trivial solution. Okay, all that said, you might be wondering, this is a conference on spatial holonomy and complex manifolds and structures. Why all that? So it's been known, it's very classical work, that this functional actually admits some very interesting absolute minimizers and also first order solutions to these equations. And these absolute minimizers are called vortices. And these happens on Kähler manifolds. And this self-duality property has to do with this. So a lemma, which, well, this dates back to, this is a Bogomolny trip type that you can rewrite your energy using the geometry of the base, and in such a way that some topological term appears, and you can see right away some absolute minima for your functional. And this was done, well, at least dates back to Bogomolny, but you can see in general for Kähler manifolds the work of Bradlow in the 90s. So if this guy is Kähler, then for every pair, you can actually rewrite the energy, maybe on that board. As follows. So this becomes 4 epsilon squared, 0 to part of the curvature. I'm using the B-degree decomposition of the manifold and Kähler identities to do this. It's just a straightforward computation. And lastly, a topological term, which, to easy notation, I'm actually hiding some factorial inside the definition of degree. So for me, the degree, by definition, is just this. So if this was not here, this would be an integer, but I'm putting this factor. And also, and so this, by Cherny-Vail theory, you can write this as a and this turned out to be the dual of the, sorry, this lambda operator here is the dual, is the metric dual of the Lefschetz operator of wedging with the form omega. So for two forms here, it's just the inner product of F with the two form omega, right? And this is just I lambda F volume. All right. As with it is the case with every Bogomolny trick, you can actually do it differently. You can change del bar by del, and this sign here by plus, and this sign here by minus, and you get the same energy identity. So what is the conclusion of this is that thus this energy is lower bounded by this topological value, and this topological lower bound is attained at some u nabla if and only if u nabla is what we call a vortex, sorry, or let me use different color here. Or anti-vortex. And this really just depends on the sign of the degree, which obstructs the existence of one solution or another. So this is the case where the degree of L is non-negative, and this is the case where the degree is. And I will say it in a moment that when the degree is 0, these two are the same, and they actually are the trivial solution. And what is the system of equations for a vortex? It's precisely when those L2 norms there vanish. Right, this is identically on M, and of course the anti-vortex here is just changing this to this and changing the sign here. All right, what's the next observation? Yeah, so I promised this remark. So remark if u nabla is a if degree of L is 0, then u nabla is a vortex or anti-vortex if and only if its energy is 0, which is the same as what we just saw. Right? Because for a vortex, these all vanish. The energy will be the degree is 0. Okay. And right, so there's, of course, this, so then that's it. The self-duality is precisely this property here of having these vortex, anti-vortex solutions. And that scale, epsilon, I will talk more about it later, but the way we scaled the energy functional is in such a way that we preserved this self-duality property. That's why the self-dual scaling of the abelian Higgs energy. Another remark is that, so Bradlow actually worked with the following energy functional. I will call E tilde tau not only Bradlow, but Taubes and others. But when you do the same trick with this functional, you actually get a tau here. So the energy of minimizers in this case is O of tau, big O of tau. And I want to normalize this. So that's why so in the end.
So the anti-vortex case, this is the one to write the first equation is F2 0. So it's conjugate converting to the first equation.
Yeah, but you have a Hermitian connection, so these two are related by a sign. Okay.
But the integrability is.
Yeah, so if one is 0, the other is also 0. Okay, so so the relation between the functionals is precisely this one. You also normalize the Higgs field. Why? Because, well, I mentioned the maximum principle thing, that the norm of U is at most 1. In this case, is at most tau. You just normalized it to be at most 1. Okay, so that's the remark. Another thing more important is that if you do this, complex conjugation creates a bijection between these two notions. So if you are in this case, and you wanted to study anti-vortex because you like the negative sign, then you just take the complex conjugate and everything will work fine. And actually, this is not just for vortex. Actually, we are going to be caring about critical points, general critical points, not only vortex. I will say in a moment that vortices are very well understood by classical works, but this transformation preserves everything which we've been talking about. So from now on, without loss of generality, I will assume we are always working in this case. Right, a definition. So U nabla is called irreducible when U is not identically 0. We are in abelian gauge theory. There's nothing more than just telling you this. And if, in case you are wondering if there's any vortex solution at all, and can you characterize them and try to classify, etc., you might have noticed that there's a necessary condition to be an irreducible vortex. which is when you integrate this equation here, you get 2 pi degree and the integral of this side. And this guy has a non-trivial L2 norm. So you get an inequality, which is 2 pi degree L should be less than the volume of M over this parameter squared. And hence the parameter. Why the parameter? Why? Because if you had epsilon equals to 1, then you would have this nonsense abstraction to have vortex solutions. And you would have to, let's say, rescale the metric so that this is true. But you don't want to do that, so you introduce this parameter so that for epsilon sufficiently small, that's OK. All right. And then Bradlow's main work was to actually show this is somehow sufficient. So Bradlow in the 90s showed that the moduli space of irreducible vortex solutions on L mod gauge is in fact in one-to-one correspondence with as soon as this condition holds, sorry. So if star holds, then you have this one-to-one correspondence between irreducible vortex solutions and effective divisors. On your Kähler manifold, modulo linear equivalence. So if you want to know if there's an irreducible vortex solution, go to your favorite algebraic geometer and ask him. Don't ask me. So how you do that? So it's just to give you a taste. This is just the map here is just the zero set of the section. Of course, you have if you have a vortex solution, this is a holomorphic section. The zero set will give you an effective divisor, and conversely was the work of Bradlow. Given an effective divisor, sorry, I forgot to mention something very important. It's not any effective divisor, but effective divisors Poincare dual to the first Chern class. Otherwise, it doesn't make sense. Okay, and so given someone on that side of the picture, you get yourself a complex line bundle which is topologically equivalent to this original one because of this condition, and a holomorphic structure and a prescribed non-trivial holomorphic section. Then what Bradlow did was, OK, so fix a background metric, Hermitian metric. Any other metric will be written as a positive function times this background metric, positive real function. And so you have an associated Chern connection to this pair holomorphic structure and Hermitian metric. And you write down this equation, the only left equation that you need to check for this metric. And you get yourself an equation, a PDE, on this function relating the metrics. And after some massage, as Jacob said last time, you can get yourself a Cousin-Warner type equation. And there will be some independent term there, which you will have to know the sign to have the existence of solution. And the sign turned out to be exactly this one. OK. So this is fairly understood. Cool. Yeah, it's true. It's true. Garcia Prada. Yeah, I should have mentioned Garcia Prada. Yeah. Anyways, well, so for instance, if you don't know much algebraic geometry, as I don't, you could look at the Riemann surface case. So complex dimension 1. And so for complex dimension 1, what you get? So you get that this moduli space turn out to be, as a set, let's say, this can be improved, but just the set of unordered DAG-L tuples of points on M. And what this is saying is that, well, if you have yourself a Riemann surface, then given any unordered set of D points, not necessarily distinct, you can get yourself a vortex, and vice versa. And this vortex will have precisely those zeros. All right. This relates to a result by Taubes. So Taubes showed essentially the same thing, but in R2 in the 80s, so earlier than this. But in R2, things are a bit different. And this will also explain a bit more this condition. So in R2, any finite energy critical point has a well-defined vortex number, which should be this integral. This should be 2 pi times some integer. The integer is the vortex number. And he proved that actually every finite energy critical point should be a vortex.
So now this is a critical point in just the ideal space, not assuming the complex structure analysis, would you say?
Yeah. And in this case, he proved precisely the same theorem that moduli space of vortices is precisely the same as the space of unordered D tuples of points of R2. So given any set of points, you can cook up your vortex. And
This discussion is always with respect to the flat metric on R2? Or?
yes, sorry, yeah, it is.
Some
Yeah.
asymptotic probably do the same result.
Well, maybe asymptotically conical, etc. Yes. Yeah. Maybe, yeah. Should be careful, Ricci curvature, etc. But yeah, so that's essentially the same. But you can see that in this non-compact setting, Taubes proved this without that condition. That doesn't make sense in R2. And this is precisely like another reason that you can think of the presence of this parameter is that in the compact setting, this thing turned out to be an obstruction, a natural obstruction. You should introduce this. Okay. So, well, I have half an hour.
No, you have to 12:50. 12:50.
Oh, really? Oh, sorry. So recent literature. I don't want my talk to be a survey. So in general, I will be very quick with this. Riemannian manifolds. There's this. So this was what was known by Gauss theorists, the Gauss theory geometric analysts in the 80s, 90s. But then this subject was resurrected by this other group of geometric analysts, the people from minimal submanifold theory. And then there's this work of Pigatti-Stern. In 2021, if I'm not mistaken. Oh, 20. And well, now that I don't have too much time, I will just maybe state in a very not so precise manner. So if you have a sequence of critical points with O1 energies, so uniformly bounded energies, which is the natural assumption since we saw this. Then what happens is that these guys turn out to concentrate energy on stationary codimension 2 varifold, whose weight measure is precisely the weak star limit of the energy measures of these guys.
Is epsilon fixed or?
Yeah, sorry. This is the asymptotic analysis when the epsilon goes down to 0. So in the end, what you get is that these energy measures turn out to converge subsequently to some weight measure of a n-2 integral, and that's very important, integral stationary varifold. And what is this varifold? It is actually, so the support of this varifold is actually the limit of the zero sets of the Higgs fields in the sense of Hausdorff topology. Come again? Yes, this is the integrand of the energy. Sorry. Right. You can actually write this later. For any. And then Pigatti, Phillips, Pigatti actually proved the converse. So in some sense, so they perceived that there's this approximation. So this is very much in the same way, the same behavior of if you pick Yang-Mills functional, Yang-Mills connections, they concentrate energy on codimension 4 minimal manifolds, and instantons will concentrate energy on minimizing, so calibrated on your geometry on special holonomy manifold, codimension 4 submanifold. And in this case, the same is true, because if you look at a vortex solution, then this guy is already area minimizing, because it's a complex variety. So the picture is essentially the same, but for codimension.
Since there's the current involved in the limit, I mean, is it really the curvature or the energy that's focusing this?
Yeah. So if you take the dual n-2 currents associated to the curvatures, this also converges to some gamma, which is an n-2 rectifiable current, etc. And at first, it will be just bounded by this varifold here. It will not coincide as sets, etc. But for energy minimizing sequences, then Parisi, Pigatti, Stern showed gamma convergence between these functionals. And so they showed actually that this gamma here, the varifold associated to this, is actually precisely the same as this. Yes. So then Phillips Pigatti actually showed the converse, given some and this is probably 21, given some non-degenerate minimal submanifolds of codimension 2, you can actually find yourself a line bundle and a sequence of these critical points concentrating energy on this. So what is the...
This is always in the context of a compact Kähler.
No, sorry. This is in general Riemannian manifolds, these results. These guys did it in very general.
Always compact or?
Always compact, yeah. But for me, I would be interested on the Kähler case, Kähler situation. And we'll cut this, blah, blah. Yeah, so initial question is, can we, probably very ambitious, can we establish a dictionary between the variational theories of this functional and the volume functional on codimension 2. So probably a more down-to-earth question would be, so in minimal submanifold theory, people try to classify minimal submanifolds according to their Morse index, right? You can try to do the same for this functional now. And you have this result, classical result by, I'm just talking about classical results, by Lawson-Simons, at least on complex projective spaces, that says that the index 0 minimal submanifolds or stable minimal submanifolds in a complex projective space must be a complex variety. The analog here, since the complex variety corresponds to the vortex, etc., would be maybe, under some assumptions, the stable critical points of this functional must be vortex. And you have results of the sort for the Yang-Mills function, for the Yang-Mills functional, like Bourguignon-Lawson works, etc. And so the question is, under which assumptions can we prove that stable critical points. So this would be the first thing to try to do in this bigger project. Are vortices. And well, there are some recent results on this. First, Darin Sheng, the guy I just mentioned in the beginning of the talk, who would think that he was thinking about this problem, right? Round S2 or flat D2. He proved, of course, again, the line bundle with non-negative degree. Suppose star, which means U nabla stable critical point. If either U nabla is irreducible or M is the round to sphere and you have this condition on the degree that is less than or equal to 1 over epsilon squared, which, if you remember with the volumes, the volume of this guy is 4 pi, so it's precisely that thing, then U nabla is a vortex. That's very nice. His proof was based mostly on methods like the methods used on Bourguignon-Lawson paper, on stability of Yang-Mills connection over homogeneous form manifolds. And then Ákos Nagy and Gonçalo Oliveira, right after, proved the following generalization, that M be any Riemann surface so Kähler manifold of dimension 1.
What's a Riemannian surface? A Riemann surface.
Riemann surface. Come again?
That doesn't fix it. Metric. So.
Well, yeah, I mean, just take yeah, so complex, so Kähler manifold of dimension 1 omega. Okay. Right, and then what they proved is assume star. So assume this, then if you are in this regime where 4 pi dag L is actually greater than the volume over epsilon squared, then U nabla is a reducible solution, i.e. U vanishes identically. So that means nabla is the only connection up to gauge whose curvature is the harmonic representative of the first-year class, blah, blah. And 2, if 4 pi dag L less than volume, then it is indeed a vortex. Okay, so let me explain briefly why this result generalized this one. I don't know if it's clear. So this first item is saying that the only regime where you get irreducible solutions is this one. So this, in this reducible case, you actually prove it's a vortex. So this part of the statement of Darin-Ching is proved by the second bullet. And in this situation, you are precisely, if you are less, you are precisely in this situation, and it's a vortex. If you are equal, then in equality, you are actually a reducible solution. In a reducible solution, so this guy is harmonic. So reducible critical point means that this guy is harmonic, which means in a Kähler setting that this function here is constant. But if you integrate this, then this constant is determined. This is 2 pi dag L volume.
For your interpretation of star, does that mean that the Hessian is positive definite, or just that it's a local minimum?
Local minimum. It's just semi-definite. Weak stable, yeah. Weakly stable for some.
A local minimum is actually a global minimum.
Yeah, precisely. That's the statement. So in this case, locally minimizer stable critical points are actually absolute minimizers. Okay. So why the equal case is also covered by this. So in the equality case, you are in a reducible case, and this guy will actually be exactly what you need it to be, which is 1/2 epsilon squared. And this means that this guy is actually a vortex. For a vortex, they are absolute minimizers. So this result is covered by Nagy Oliveira. And now let's go to my results.
That dates back to Nash.
Nash?
Yeah, Hungarian. Maybe he doesn't say it that way. No? What you get under 40 to say it correctly? Nashi?
Ah, yes, sorry about that for butchering the name of people. Akos is a good friend of mine. Sorry, Akos. Well, so development. Theorem. Suppose you have any Kähler manifold. Closed Kähler. Degree positive, okay. Assume U nabla is an irreducible critical point. The neither less than this function. Everywhere. Or U nabla is a vortex. This is the first result. Why it's important? Well, in particular, it generalizes bullet 1 of Nagy-Oliveira, right? Because, of course, the norm bounds I lambda f. You integrate, you get that if you have an irreducible critical point, you must be in the second regime right there. So in the greater than or equal regime, you just have reducible solutions.
But you're not assuming stability.
I'm not. And should I go to parts of the proof or next results? how much time I have left?
You have -1 minute.
Oh,
Decide how to use that.
can I just state one more theorem, maybe?
Please.
Yeah, it's okay. So same hypothesis. This is about the stability of the reducible solutions. Okay, I understand what happens in all the regimes. So if you are in this case, then let's denote the reducible, the only reducible solution like this. So recall that it is the only critical point in this case by that result, and it is not a vortex, but it is stable. So this is one friendly reminder that you should consider additional hypotheses, because otherwise maybe stable critical point will not be a vortex. And 2, let lambda 1 be the infimum of the spectrum of this guy. Then it's well known, I guess, that this is lower bounded by this with equality if and only if the connection is actually inducing a holomorphic structure and the holomorphic sections are the lambda 1 eigenvalues, eigenfunctions, eigensections, sorry. And suppose lambda 1 is bounded by 1 over epsilon squared, 2 epsilon squared. Which implies we are in this regime then this is still the statement is true in this case. So it's not a vortex and it's unstable. And in fact, you can prove a little bit more. You can prove lower bounds for the Morse index of this guy. It's so if epsilon is sufficiently small, depending on the spectrum of this operator, So for any natural number you give me, I can find a sufficiently small epsilon so that the Morse index of this unstable critical point is at least n. And sorry, I should stop here. Thank you very much.